Okay. So we are in class number 18 today. We are going to be talking about memory reliability and cache coherence. So these two are very interesting ideas and something that is going to kind of complete our discussion on memories, right? So this is our fifth and last um, sort of lecture in terms of memory. And from the next class onwards, we will get into operating systems. So memory reliability and cache coherence, that's what we are talking about. Before we get into the lecture content, I want to make a couple of announcements. One is our second exam for the semester is on Monday, April 5th. If you guys have not looked at the resources that are posted on Piazza, please take a look. It has logistics, it has a back exam, and the solution to the back exam. So take a look on about that. Logistics are going to be similar logistics to exam one. So that's coming up on Monday. We are also going to have a wellness day for CANOS on Thursday, April 8th. Now, this is something that the department, in fact, the whole institute is feeling the need for, and rightly so. Everybody, the students deserve a break. The faculty deserves a break. Everybody is sort of um, missing having a spring break. So I think this is going to do us a little bit of good. Even if it is one day, we still get to, get that one day break. So on Thursday, April 8th, so that's 1 week from today, we are not going to have any class. We are not going to have any activity. So please use that time to sort of relax after the exam. And then when we come back on Monday of the following week, we will, uh, you know, do an introduction on operating systems. Questions or concerns about this? I hope you guys can really take advantage of that one day break. I know I am going to have some downtime, which I will appreciate. Okay, no questions or concerns. So that's good. We will start with memory reliability, right? So, how reliable is our memory? We said our memory is going to have multiple layers, like the topmost layer is our cache, the second layer is the physical memory, the RAM, and then way down we have the hard disk or even the server, right? So we have a memory hierarchy that we have been talking about, and so far we have sort of assumed that everything is reliable, meaning everything that we write into the memory is going to stay there as is. It's not going to change with time, or it's the memory is not going to forget. That's the assumption that we have been making. But the reality is, after you write certain bits to the memory, after you have written certain words to the memory, you might have errors over time, which means that after you read, some time goes by, and then you try to, sorry, after you write, some time goes by, and then you try to read the same memory location, it might not be the same as what you wrote, right? So if we want a fast memory, we want a reliable memory, but even if our memory is very fast and unlimited, but if it is not dependable, if it forgets, then it's not very attractive. I hope you guys all can relate to that. Now, how do we build reliability in our memories? Well, we are going to use some redundant bits. So we are going to leverage redundancy to make nearly unforgettable memories. So the whole idea of this lecture is going to be, if while writing and then reading the memory location, can we detect some errors? can we correct certain errors? So we will focus on error detection and correction. So that's what we are going to be talking about today. Now, the redundancy can be built in several different ways. The one algorithm we will be looking at is Hamming error correction codes. So for that, we need to introduce Hamming parity codes. And the moment you hear parity codes, it should ring a bell from Coco about what a parity code is, right? So you're looking at the number of ones in a word, and you're just counting the number of ones in a word. And if you have the number of ones in a word to be an odd number, then we are going to call that a odd parity code. Or if the number of ones in the word are even, all right, the number of ones are even, then it's going to be called a even parity code. So we can take like a very simple 4-bit word, and let's try to find out whether it is even parity or odd parity, right? So let's say 4-bit word is 1011. This is of course in binary. So what would be the number of ones? Well, in this case, you are seeing too big. 1, 2, and 3 ones, right? So if you have 3 ones, that is going to indicate odd parity. You guys see that? So that number of ones in the code word. Now the code word could be 4 bits, could be longer, but just to give you a sense of what parity, how is parity computed, I'm giving you a very simple example of a 4-bit word. Just count the number of ones, and that's going to indicate whether it is odd parity or even parity. Odd number of ones, odd. Even number of ones, even parity. Now, when you actually try to store the data or write the data to memory, you are not just going to write the 4-bit word. In fact, you are going to write a 5-bit word that also includes one parity code. Now, this is just a simple discussion to build up some motivation towards Hamming codes. The idea is you would write some redundant bits, right? It could be one, it could be more than one redundant bits. Here the example is for 1 bit. So when a word is written into memory, the parity bit is also going to be written. And that parity bit is going to be 1 for when it is odd, 0 for when it is even parity, right? So in our case, we have a 4-bit word which is 1011, right? So that's our 4-bit word. So what would be the parity bit? I will use small p to find out the parity. What would be the parity bit in this case? 1, right? So it's an odd parity situation. If it's odd parity, the parity bit or the redundant bit is going to be 1. So instead of writing 4 bits, I'm actually going to write a 5-bit word to the memory, which is going to be 1011, the 4 bits from the original 4-bit word. And then at the end, I'm going to pad it with my parity bit. Now, this doesn't necessarily need to go all the way to the right. It could be at certain other location. I'm just using an example of putting the parity bit all the way to the rightmost bit. Now, when you read this guy, right, you have written it. Now you have written the 5-bit word into memory. You have written 10111. Now when you read it, you are going to read the n plus 1 bit word. And the parity of that n plus 1 bit word is always going to be even. You guys see that? So when you read this 5-bit word, you are going to get 4 ones, an even number. It is always going to be a even parity code that you read. It works even for the original word. If it had even parity, then you would pad it with a 0, which again leaves it as a even parity code. So you have a few data bits, you're trying to pad it with parity bits in such a way that the entire code, right? So let's try to identify these by names. this guy is going to be your data bits, right? And then this guy is your parity bit. And this guy is what we are going to call a code or a code word. So when you write a code word into the memory, you're writing data bits and you're writing the parity bit as well, but every code word is going to have even parity. What that means is when you read it back from the memory and for some reason you get an odd parity code word, you know errors have occurred, one or maybe two or maybe more than two, right? But if the code word has even parity when you read it, it is going to tell you that error has not occurred. But let me challenge that statement a little bit. If you read a code word and you see it as even parity, does it guarantee you that error has not occurred? You guys are right. It doesn't guarantee you that the error has occurred. You still may have error. Why is that? Why is it that you read an even parity code word and you're still confused whether even number of bits may be wrong? You are absolutely right. So if you have two errors or four errors, you may still get an even parity code word being read. But one thing that is helping us over here is that the probability, the chance. So there is an important note over here. And the important note is the probability of 1-bit error is much greater than probability of 2-bit errors. And that's even greater than probability of 3-bit errors and so on. So the highest chance of something going wrong is probability of 1-bit error, right? So 1-bit error is most likely scenario, and which is why we are trying to develop some codes here, specifically the Hamming error correction code, which can go in and detect that 1-bit error and also be able to correct it. But it would, as you may imagine, it would also be helpful to know whether two errors have occurred or not. So we will start with 1-bit error correction, detection and correction, but we'll also talk about a scheme very briefly that will allow you to detect two errors. We will not be able to correct the two errors, but we will at least be able to detect that two errors have occurred. All right, questions so far? This is going to get interesting. If you have not seen Hamming codes in any in other classes, this is going to get very interesting for you. No questions? All right. So let's talk about the parity code, and here we are focusing on error detection. We need to talk about a few examples here just to understand the basics so that we are ready for a deeper conversation about Hamming error correction codes. So first we'll talk about Hamming distance, right? So that's the first question. What is the Hamming distance of the bit patterns that are shown below? Hamming distance is essentially the number of locations, number of bits that are different. This is number of bits that are different. And we are trying to compare how many per location, how many bits are different between two code words, and that is going to define your Hamming distance. And as you may imagine, this has to be an integer. So how many bits are different over here? Well, you guys can, I hope, see that in There is a error. There's a it's different over there, different over there, different over there, and all the other bits are exactly the same. So the Hamming distance between these two codes is going to be 3. Right? You're simply finding out at a specific location whether they are same or not. The number of places they are not the same, they are different. That's going to give you Hamming distance. Pretty easy so far. All right, let's go to the next point here, which is show the 9-bit pattern used to store 42. 42 is being expressed in decimal, and we are trying to show that the 9-bit pattern, not the 8-bit, but the 9-bit pattern is all of these bits in binary, and that's what you're trying to store in memory. What we are going to assume is that the words are written to memory with even parity, right? So whenever you write the code word. Code words that are written to memory are always going to have even parity. And the parity bit is located all the way to the right, just as we did in our 4-bit word example. So what is 42 base 10? Can we generate a 8-bit data for that? Let me do that decimal to binary conversion quickly. It is going to give you 0, 0, 1, 0, 1, 0, 1, 1, right? So that's 42 in binary. And now we are going to find the parity of this code. Is this even parity or odd parity? Oh shoot, this should be 0. You're right. 1, 0, 1, 0, 1, 0. That's right. Thanks for catching that, you guys. All right, so now let's see. What is the parity of this guy? Is this even parity or odd parity? Odd parity, because I have 1, 2, 3. 3 ones, right? So if I have 3 ones, that's odd parity, which means my parity bit is going to be 1, which is what I'm going to pad all the way to the right. And I'm indicating that in red color. So that's your 9-bit code word that you're writing. And, this is exactly matching the guy. Oh, hold up. This was 42, and this is the 9-bit pattern that we are using to store that 42 with one parity bit. So the number of data bits or the useful bits are 8. One of them is redundant, the parity bit, which both combined you are generating a 9-bit code word that you will eventually write to memory. All right, next question is, you are reading a certain code word from memory. The question here is, should the system signal an error? How are you going to know whether error has occurred or not? Well, you simply look at the parity, right? The answer, Rojan, is absolutely right. It is yes, because you have odd parity in the code word. Let's see. 1, 2, 3, 4, 5. There are 5 ones in this indicating odd parity. So yes, of course, some error has occurred. I don't know how many errors have occurred, but I definitely know that error has occurred. And the reason for that is that the 9-bit code word has odd parity. Now, that didn't work out. So let's try to see what would happen if the question was slightly different. If this is your 9-bit code word that you are reading from memory, should the system signal an error? Well, again, we are going to do the same thing. Let us go in and try to see how many ones do you have. There are 2 ones in this code word, which means it is even parity, right? So if it is even parity, then the system is not going to signal an error, but we know that some error has obviously happened, right? Because our code word was all of this 0, 0, 1, 0, 1, 0, 1, 0, 1. We are not reading that, we are reading something else, right? So we know that some error has happened, but the system is not going to signal that because it is still even parity code. what can I do? What can I do here if I wanted to um, know if an error has occurred, and if I wanted more insight about, which bit is an error? What would I need to do? I hope you guys agree that I should not, I cannot go changing the number of data bits, but perhaps I can think about increasing the number of parity bits. So instead of having just one parity bit protecting 8 bits, if I had more number of parity bits protecting the same number of 8 data bits, I may be able to find out more about where that error has occurred. Do you guys see that? So one parity bit is not benefiting me too much. But if I had more number of parity bits, then I would be able to. But again, more parity bits with a very good scheme will help me to find out more about the number of errors that have occurred. So one parity bit is not working really well. All right, let's talk about correction. Hamming came up with this Hamming error correction code, in short ECC, error correction code. And there are some properties about this Hamming error correction code. The first property is that Hamming distance between any two code words that you're trying to write to memory is going to be 3, right? So the minimum distance is going to be 3. So let me just write that down. This means minimum Hamming distance that is the number of locations in which things are different. Minimum Hamming distance between any two code words is 3. That's the minimum. You can have it at 4, you can have it at 5. So 5 things can be different, 6 things can be different, but you cannot go down to 2, right? So that's sort of the property of this code. And the reasoning behind this particular limitation of Hamming distance being 3, at least 3, is that if you have single bit error, then if you have single bit error, so let's see, you have a code word and you have another thing that you're comparing with while you are reading it, you have code word with one error, right? Between these two guys, between this and this, what is the Hamming distance? One. That's right. Because only one bit is a problem, right? So you see here, between the code word and the code word with error, the Hamming distance is 1, which means that it is still closer to any other code word, right? So if I draw another circle here and say any other code word, what is the distance there? Minimum. The minimum based on the limitation is 3, right? So even if I have one error, the code word with the error is still closer to the original code word than any other code word, which is why this can work. You guys see that? So all of that explanation is sort of captured in that second bullet over here. If we used a code word that has a minimum distance of 3, then any single bit error would still be closer to the correct pattern than any other valid pattern. So any other valid pattern is over here at a minimum distance of 3. But if you have a code word with one error, it's still going to be closer to the correct pattern, which is right here, the one that we started off with. You see that? So that's why that limitation is present here. Minimum, at least you need 3 places to be different between the code words. All right. Now, next, extra parity bits, not just one but many, are used to allow the position identification of a single error. This is single error correction code. So, of course, you have to detect it too, but single error detection and correction code. We are going to use many parity bits to allow us to figure out where that single error has occurred. Now, in terms of code word length, how big our code word can be, it is going to be related to the number of redundant bits we are trying to use to protect that code word. So if I use R bits as redundant parity bits, then the maximum code word length I can use with that in order to be able to correct one error is 2 raised to R minus 1, where R is an integer greater than 1. So for example, suppose I have four bits, right? 4 parity bits. If I use 4 parity bits, how big can my code word be? I'm using 4 parity bits. How big can my code word be? That's right, 15 bits. 2 raised to R minus 1. Okay, so if my code words in all of the Hamming codes that I can have is as big as 15, how many data bits? So this tells me how many data bits can I protect? This should be easy. There are 15 bits in the code word. Each code word is a combination of data bits and parity bits. Total there are 15. 4 are being used for parity, so 11. That's right. There you go. So, and this is the maximum, right? So of course you can use fewer than that. With 4 parity bits, you can have like 12 bits for total code word and 8 data bits. But that's sort of your limit with 4 parity bits for single error correction. Questions so far? Would you mind showing the last slide again for a second? Sure. There it is. No problem. All right. We are taking questions over here. Okay. Now let's try to get into the algorithm itself, right? So let's try to see what are the steps we are going to need to calculate the Hamming error correction code. So the goal is the user gives you data bits, right? User provides data bits. Then based on Hamming ECSE, you generate parity bits. And then by using both of these, you construct a code word. And that's what you will write to memory. Construct a code word to be written to memory. So that eventually when you read it back, you will read the code word back. And because you have taken the data bits and protected them with parity bits, when you read it back, the claim by Hamming is that you will be able to detect and correct one error. More than one you cannot do, but with the number of bits that we have been talking about, right, r and 2 raised to r minus 1, you will be able to do a 1-bit error correction. So that's sort of the goal here. Let's start talking about what are the steps involved in this. First, you start numbering the bits from 1 or on the left. So you see, I have at the top of this table here, there is a bit position. The bit position is not starting from, what we typically do, like bit position 0, 1, 2. Just to use bit 1, bit 2, bit 3, we are starting this position with a 1. So bit position 1 all the way to bit position 15. Why is this 15? Because you guys said code word length should be 15. The code word itself should be a combination of parity bits, that are redundant bits, and data bits. But to all total, they are 15. And for this particular example, I'm using 4 parity bits. Where are the parity bits going? You see, parity bit 1 goes in position number 1. Parity bit 2 goes in position number 2. Parity bit 4 goes in position number 4. Parity bit 8 goes in position number 8. That's it. Those are my 4 parity bits going into those specific locations. What are those? 1, 2, 4, and 8. Powers of 2, right? So your parity bits, in other words, your redundant bits, are going into locations that are powers of 2. So mark all the bit positions that are powers of 2. 1, 2, 4, 8, 16, and so on. In our case, we don't even need 16 because there's no 16th bit here. 1, 2, 4, and 8. Only 4 of them for us, right? So just let me talk about parity bits in locations 1, 2, 4, and 8. Those are going right here. Let me use this. 1, 2, 4, and 8. I don't know them yet, right? I've not generated the parity bits yet. So these are that's your encoded code word. I know the data bits because the user gave it to me, but I don't know P1, P2, P4, P8 yet. I need to still generate that. I need to find that out. What does P1 cover? P1 covers 1, 3, 5, 7, and so on, all the odd positions. P2 covers 2, 3, and so on. I'll talk more about where this is coming from in just a bit. But I hope that we are in agreement in terms of where the parity bits should go. P1 in 1, 2, 4, and 8. Powers of 2. Those powers of 2 bit positions, right? And then all the other bit positions are going to be used for data. In our case, 3, 5, 6, 7, all 9 through 15. All of those are data bits. And because how many data bits are there? Maximum of 11, right? So that's your 11 bits. D1, D2, D3, D4, D5, all the way to D11. Those are your user provided data bits. All right. Now let's talk about the parity coverage a little bit. I'm going to use P1 to cover all your alternating bits. I'm going to use parity bit number 2 to cover the locations 2, 3, 6, 7, 10, 11, and 14, 15. 4 for 4, 5, 6, 7, 12, 13, 14, 15. And then P8 will cover 8 through 15. And by doing this, each data bit is being covered by at least 2 redundant parity bits. As you can see, D1 covered by 2 parity bits, D2 2 parity bits, D3 2 parity bits, D4 3 parity bits, and so on. So at least 2 parity bits are being used to cover each data bit. All right, let's talk more about this. Let's continue our conversation on how do you calculate the Hamming error correction code. The position of the parity bit determines the sequence of data bits that it can check. And the figure below shows this coverage graphically, meaning bit 1, your parity bit 1, P1, will check bits 1, 3, 5, 7, and so on. What is so unique about these numbers 1, 3, 5, 7, 9, and so on? Well, for all those numbers, the rightmost bit in binary is a 1. Rightmost bit equals 1. 1 is 1, 3 is 1, 1, 5 is 1, 0, 1, 7 is 1, 1, 1, 9 is 1, 0, 0, 1. The rightmost bit is always 1 for all those positions. That's what P1 is doing. It is covering all those numbers, all of the odd positions. And then bit 2 or P2 is going to check for 2, 3, 6, 7, 10, 11, and so on. Those are highlighted by crosses over here. What is so unique about those numbers? Well, the second to the rightmost bit is always 1 for those numbers. Second to the rightmost bit equals 1. And similarly, for 4, the third bit is going to be 1. For numbers 4, 5, 6, 7, 12, 13, 14, 15. And you can verify this. And for similarly for bit 8, you are going to get a 1, 0, 0, 0 here, which essentially means the most significant bit, the leftmost bit for all the numbers is going to be a 1 for that, which starts from 8 with 1, 0, 0, 0 all the way to 15, which is 1, 1, 1, 1. You guys see that? So by doing all of these things, we are covering each bit by 2 or more parity bits. Each data bit is being protected by at least 2 parity bits. Now we are going to set the parity bits such that they create even parity for each group. So we are going to determine P1, P2, P4, P8 in such a way that each group is going to have even parity, because we still need to figure out what the parity bits are. All right. The next question is, how do we know if there is an error? You know what? Let me just take questions here. How are you doing so far? We are going to go through a very detailed example about this. So we'll try to come up with some 11, or fewer. We'll start with 8 data bits, arbitrary 8 data bits, and then we'll try to compute P1, P2, P4, and P8 for that. We will generate the code word, we will put it into one error situation, and then we'll see whether we can detect that or not and correct it, of course. All right. So how do we know if there is an error? We have generated each parity bit by assuming that the group is even parity, right? So the group along with that parity bit is going to have even parity. So for the code read from memory, when you read the code word that you stored in memory back, you are going to check the parity of each group. If the value of the 4 parity calculations, which is P8, P4, P2, and P1 is 0, 0, 0, 0, that essentially tells you that no error has occurred. P1 even, P2 even, P4 even, P8 even. So when you read the code word and when you recalculate your P1, P2, P4, P8 bits and all of them are 0, that means that no error has occurred. However, when you read the code word back and you look at the parity bits, you calculate the parity bits again, P8, P4, P2, and P1, and if that for some reason comes out to be 1, 0, 1, 0, right? So in this case, P8 is 1, P4 is 0, P2 is 1, P1 is 0, which is 10 in decimal, then the Hamming error correction code tells you that the bit number 10, which is D6, is in error. You can see bit position 10 is where we are storing the 6th data bit. That is in error. You see, this position is being covered by P2 and P8. So if you get a 1 and a 1 for P8 and P2, which you see it adds up to 10, that tells you that the error is in the bit position 10, which here is D6. So once you know that there is an error, all you need to do is convert a 0 to a 1 or 1 to a 0, and you would have corrected it. Just flip that bit. All right. So correct the error by inverting the value of bit number 10, bit position 10. That's how you would fix it. All right. So I think we are ready for the example, and the example is going to kind of open up all the confusion. If there is any confusion, it's going to be all clear, hopefully. All right. So let's try to assume 1 byte data value. So this is sort of our user provided data bits. User provided data bits. There are 8 of them. 1001, 1010. I am required to store this into memory safely. So what I'll use is a Hamming error correction code with 4 parity bits, so that when I read it back, I will be able to correct 1 error if it happens. My goal over here is to show the 12-bit Hamming error correction code. What am I going to store in memory? I know the data bits, but I need to generate the parity bits so that I can put the code word into memory. I can store that, right? So what I'm going to do is I'm going to start off with leaving some blank spaces for the parity bits. So leave spaces for parity bits. We are going to get a 12-bit pattern here. Why 12-bit? Because we have got 8 bits from data and we have 4 bits from redundant parity bits. What is that going to be? Let me just put some blanks here for parity. I've got 2 blanks for parity bit 1 and parity bit 2, P1, P2. I need to find those out. Followed by a 1 from the first data bit. Then I've got P1 is done, P2 is done, 3 is done, P4. So P4, again a blank with P4 that still needs to be computed over here. Is R always 4? Not necessarily. It depends on the code word that you're trying to protect, right? So in our case, we are using a 12-bit code word. You can have as much as 15-bit code word with R as 4. If you need higher than that, then you need to increase R. So for example, if you have R as 5 bits, 5 parity bits, then you can go as high as 31 code word length, which means that you can protect 31 minus 5 data bits. You see that? So the more number of data bits you want to protect with this SEC scheme, the more parity bits you will need. All right, let's see. We have done with P1, P2, 3rd bit position is done, 4th is done. Then we have a few data bits. So the next 3 data bits are what? 0, 0, 1 from here. Then we have got our last parity bit. What is that? P8. I need to still compute that. Then I've got all the data bits remaining. What is that? 1, 0, 1, 0. Right. So I'm just going to write that at the end. 1, 0, 1, 0. So that's essentially what my code word, 12-bit code word is going to look like. I still need P1, P2, P3, P8. P1, P2, P4, P8. I still need to calculate that. So for that calculation, what I'm going to do is I'm going to write some statements over here. Position 1 checks for what? Checks bits 1, 1, 3, 5, 7, and so on. How many ones do you see in those locations? So let me just highlight those locations here. 1, 3, 5, 7. So a little bit bigger is fine. That, 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 that. Alternating. Well, P1 is what I'm trying to find out. So I'm going to erase the thing over there. What about all the others? How many ones do you see over there? 1, 2, 3, 4. There are 4 ones in that group. You guys see that? 4 ones. If you have 4 ones, is it even already or odd? 4 ones indicates that you're already even parity. That's right. So what should be P0? P1? 0. That's right. You already have an even code for that group. So I don't need P1 to be a 1. I'm okay with it being a 0. So I'm just going to erase this guy and write a 0 in blue. You guys see that? And that's sort of the same thing that you are going to apply for all the other positions. Just repetitive from here on out. So I'll try to go fast here. Position 2, then position 4, and then position 8. And then as I go along, I'm going to erase that, erase that. I don't know the number of ones. I don't know these guys, and I don't know those guys. So this is going to be position 2, position 4, and position 8. It is going to check for bits number what? This is going to be 2, 3, 6, 7, 10, 11, and so on. So what are those? Let's see. Erase, 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 erase. How many ones do you see in 2, 3, 6, 7, and so on? So I'm not going to put a thing on P2. So I'll start with 3. 3 is done. 2 blanks, and then 2, 2 blanks, and then 2. All right. How many ones do you see in the second group? 1, 0, 1. So 1, 2, 3. 3 ones, right? 1, 2, 3. 3 ones. So if you have 3 ones, what should be P2? P2 should be a 1 because I have to make the group even parity. I had odd number of ones, so if I made P2 a 1, that group will become even parity. So I've done with P2. Erase and put it in. For 4, what is that going to check for 4? This is going to be 4, 5, 6, 7, 12, blank, blank, blank. What are the bits there? So erase, need to kind of get away from that and then start with 4. So let's see. 1, 2, 3, 4. And then blank, 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 blank. That. How many ones do you see here? I'm trying to compute P4, so I'm going to not mark that. I see only 1, 1. Right? So let's see. 1, 1. So P4 should be what? Can you restate how to determine which bits? Sure. So you see, can you restate how to determine which bits are checked for which position? I think this table will tell you all of it, right? So parity bit 1 will check for 1, 3, 5, 7, 9, 10, 11, 13, all the odd ones. And then P2 will be 2, 3, 6, 7, 10, 11, 14, 15. all the numbers in which, all the decimal numbers in which the second to last, second to the rightmost bit is 1. So, I wouldn't recommend you guys to sort of do this by memory. I would just recommend you to use this sort of a table for reference. All right, let's go here. Right. So we talked about P4. We generated P4 to be a 1, right? So this guy was odd parity. We need P4 to be a 1. So let's erase this guy, put a blue one there. Done. P8. What does P8 check for? Checks for 8, 9, 10, 11, 12, blah, 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 blah. I don't even need that. So 8, 9, 10, all of those. Let's highlight those before I get rid of this. So let's see. In blue, I've got from 12. 1, 2, 3, 4. That I need to find. And then what else? So that's total of 12, right? So 12, 11, 10, 9, 8. That's it. So how many ones do I have? Over here, I have 2 ones, right? This guy and this guy. 2 ones. So what is P8 going to be? 0. And I am done. That is going to be my 12-bit Hamming error correction code that I'm going to write to memory for this particular user provided 8 bits. All right, questions about this example? So I hope so far you've kind of seen it work out systematically, but the sort of the real power of this code can really be put to test after seeing an error, like after deliberately putting an error into the code word. You will see how easy it is to detect and correct single error. All right, no questions here? Okay, so what we are going to do is we are going to take the same 12-bit code word and we have written it over here. So that's the code word from before, highlighted in blue from the previous slide, from the previous computation. And we are going to deliberately, so suppose that this is what we write to memory, right? The code word. And then when we read it, suppose we have an error in this particular location. You see that this is 0 here, but what we are reading is a 1 here, right? So suppose we got an error. Now using this corrupted code word, we need to figure out where is that error and be able to correct it. So let's see whether we can do this using the Hamming error correction scheme. Let's see if we can find and correct the single bit error. Of course, it has occurred over here that we are marking in red. So what we are going to do is check group by group. So our first group is going to be what? Group 1. Our group 1, well, let me write the entire 12-bit code word here, which is 0, 1, 1, 1, 0, 0, 1, 0, and then 1, 0, 1, 0. That's my group 1. I'm going to highlight in blue. So what is group 1? All the odd locations, right? Odd locations alternating. So what is the parity of this guy? How many ones do you see here? 1, 2, 3, 4. 4 ones. 4 ones. Does it make it even parity or odd parity? 4 ones are of course even parity. Even parity means you're okay. You don't have an error in group 1. All right. Now let's go to group Let me not do this. Let me take the whole thing and copy this. And I'm doing this for group 2 now. Different number of bits, different bit positions need to be highlighted. And I don't know if it is even parity or not. I don't know if it's okay or not. And I not counted the number of ones. But I do know that this is group 2. In group 2, what do? You do 2, 3. So let's do 2, 3. Leave 2, mark 2. Leave 2, mark 2. All right. Oh no. All right. So hold up. We need to work this using the error word, right? Not the correct word. This is 1. It was in error. So group 1 doesn't change, but group 2 will change. Because these two, right? Yeah. You see that? I hope you guys caught that change. I was working off of the correct code. No. It has already gone through a error. I need to be able to go from the error back. So I need to use the corrupted code here to be able to correct it. So I've changed that location here. It didn't make a difference for group 1, but it does make a difference for group 2. All right. So how many ones do you see here? 1, 2, 3, 4, 5. 5 ones. Even parity or odd parity? Odd parity. Odd parity means there is an error in this group. All right. Next, we need group number 4. But I also need to change that. I need to highlight things differently. 4, that becomes a 1 because of that. All right. Now let's highlight the positions for group 4. It's going to be 1, 2, 3, 4, 5, 6, 7, and then leave 4. 1, 2, 3, 4, and then that. I hope you guys can relate to filling out a truth table with this approach, right? Like this is the least significant bit, and then the next two least significant bit. That's exactly what we are following here. All right, let's count the number of ones. 1, 2. That's it. Two ones. So 2 ones are in this group. So even parity, which means this is okay. So group 1, okay. Group 4, okay. Group 2 is a problem. Now we have one more group to sort of do this for. So I'm going to resize this, make it a bit smaller so that we have space for the last group here, which is group number 8. Don't know. All right. Group number 8, there's a 1 there. Okay, so let's try to highlight from the back. Here, and here. So 8, 9, 10, 11, 12. How many ones do you see here? I've got 1, 2, 3 ones. Yeah? 3 ones, which means odd parity, which means error. So which two groups were in error? You had an error in group 2 and group 8. You see that? So error, I can write it at the top here, error in P2 and P8, which means your error corrupted bit is 2 plus 8, which is bit position number 10. What is bit position number 10? That is exactly the same bit position over here. So you just fix that one bit and you will get your corrected code. So you can leave everything else as is, 0111, 0010, 1, and then you flip that bit, 0, 1, 0, and you have corrected it. You guys see that? All right, questions about this process? So quick question. If bit position 12 was in error, which groups would have resulted in odd parity? 4 and 8. That's right. You guys got it. As simple as that. Okay. We will move on since there are no questions here. Okay. So there is a slightly different code by Hamming that we are going to briefly talk about. We are not going to do detailed examples as we did for the one before. But this is single error correction, double error detection. So you will be able to correct one error. However, we will know whether two errors have occurred. So this is single error correction, but with this code you will also be able to find out double error detection. Of course, if you want that, then you obviously need more parity bits, and that's what we are doing. We are adding an additional parity bit for the entire code word, and we are calling that Pn, P sub n. Our Hamming distance, the minimum Hamming distance between any two code words is going to go from 3 to now 4. And the way the decoding for this is going to work is we are going to use H as all our parity bits. So H will be P8, P4, P2, P1. So that's going to be your H. H is simply your parity bits, the redundant bits. Now, with this new H and this new parity for the overall code word, you can have 4 different possibilities. One is H is even, which means the parity of these 4 parity bits is even, and Pn, the parity of the entire code word, is even. If H is even and the parity for the entire code word is even, that signifies no error while decoding, while reading. If H is odd and Pn is odd, if they are both odd, then you will be able to correct single bit error. If H is even and Pn is odd, then there is an error in the Pn itself. And if H is odd and Pn is even, that will tell you that 2 errors have occurred. We will not be able to correct any of them, but we will know 2 errors have occurred. So that's sort of a quick discussion on what a double error correction code could look like with one additional parity bit for the entire code word while monitoring the parity of the parity bits. Right? So H is like the parity of the parity bits. Parity of parity bits. And that's what you see in DRAM, which uses SEC or DED, double error detection with 8 bits that are used for protecting 64 bits, for 64 data bits. All right, so that was a very brief discussion on double error detection. The next thing that we are going to talk about is sort of the second half of our lecture today, which is cache coherence. And we need to talk about the problem first, and then we can start talking about what a solution could look like, right? So the problem over here is that caches are looking at some data that is being shared by multiple caches. So for example, let me talk about this particular view here. So the logical view to a user is what? You have a very, very big memory system. Maybe you have, a memory hierarchy that is leveraging virtual memory. If you're using virtual memory, then you sort of look at a very, very big view, like the illusion of having a really big memory system, which is being accessed by multiple processors, multiple CPUs, multiple cores. So processor 1 has access, 2 has access, 3 has access, and 4. Each of these are CPUs, processors, right? So all processors have access to the memory system. That's your sort of the logical view. But in reality, what happens is processor 1 has a very expensive private cache right next to the processor, very, very nearby, which eventually has access to your physical memory. And the same thing for processor 2. Processor 2 has a small and expensive private cache right next to the processor, which again has access to this shared memory. And similarly for processor 3 and processor 4. So the dollar sign here is sort of indicating that you have a expensive private cache. Right. So let me just, this is expensive private cache for processor 4. So of course this is cache money, yes. So what could happen here is this. So suppose P1 tries to read the memory, right? So when P1 tries to read the memory, what is it going to do? It's going to look into the cache. If it doesn't find it in the cache, it will try to bring it from the memory. If it brings it from the memory, a copy of that is now present in the private cache of processor 1. And P2 could do the same thing. P2 could read the same memory location, try to find it in its cache, not there, bring it from the memory into the private cache of P2. So it could happen that the same memory location is present in the private cache of P1 and P2. So what would happen if P1 changes or writes to that memory location? Well, they will change it in their own private cache. And if it is a write through cache, then they probably will also update the memory. But what about what is present in P2, in P2's private cache? This is not going to be in agreement with whatever is in the private cache of P1 and also in the memory, leading to the problem of inconsistency for the same memory location, which is what we are talking about here. Cache incoherence is going to happen. So you guys see what the problem is here. So the problem is going to arise when there are multiple physical copies, the way we said, physical copy in private cache 1, physical copy in private cache 2. The problem is when there are multiple physical copies of one memory location and some processor is trying to write to their private cache copy. So that's sort of the problem here. Let's try to see if we can answer this question. Does this become the cache coherence problem? Is it going to exist in a uni-processor system when there is only one processor? There's only one processor, one cache, one memory. Right? So the answer over there is no, right? So the problem becomes when you have multiple processors with multiple cache. So remember this, the whole idea of having a cache is so that the CPU gets the information right away. And if you want it right away, you got to place it right next to the processor, very, very close to the processor, in order to have that very, very high bandwidth between the CPU and the cache. So that's what we are using cache for, so that we reduce access time. But because each processor will now have a private cache in the case of multi-processor systems, each private cache could be changed and lead up to this cache incoherence problem. We need a way to have everything to be consistent. And there are some algorithms we will talk about, two of them today. Both are hardware solutions. All right, let's take a look at the problem in a little bit more detail. Let us say we have a single memory location X, and we are trying to read and write to that memory location using two processors, processor A and processor B. Both these processors are trying to read and write to the same memory location X. And initially we are assuming that neither cache, neither the private cache of A nor the private cache of B has the value of memory location X. And we sort of initialize that X to have a value of 0. Now, after the value of X has been written by A, what is going to happen? You see, let's go to this table here and talk about a few things. One is, in the leftmost column, we are monitoring the time step. In the next column, we are talking about the event and who initiates that event. We are while those events are happening, we are monitoring the private cache contents of CPU A, private cache contents of CPU B, also the contents in the physical memory for that location X. So in time step 0, you have sort of initialized that X in physical memory to be a 0, right? So that's just initialization of location X to be a 0. Nobody is doing anything here. No processor is reading or writing. In time step 1, let us suppose CPU A reads X. So CPU is going to say, all right, memory, can I read location X? And as we have assumed, it's not there in the cache, right? So it's going to, CPU A is going to try to read it from its own private cache. It is going to be a cache miss because it's not there in the private cache of A. So it's going to have to fetch it from the memory. When it fetches it from the memory, that 0 is going to be copied over to the private cache of A. So this sort of comes from here, right? Right. Next, in time step 2, CPU B is going to try to read X. Again, CPU B is going to first try to access its own private cache. It's not going to find it over there. So it's going to, try to read it from the, it's going to be a cache miss. It's going to try to read it from the memory. When it reads it from the memory, again, because there's a 0 there, we have not changed it, it's going to read a 0 there. And so that is also going to be a 0 there from the memory. So now both cache A and cache B have a private copy of location X. So far only reading is happening, so not a problem. Everything is consistent. Everybody is saying that X is 0. However, what happens in time step 3? Time step 3, CPU A stores a 1 into X. So it is CPU A is writing a 1 into that memory location X. So it is only changing its own private cache. If it changes only in private cache, contents in CPU A are now going to be 1. Private cache of B is not changed. But if it is a write through cache, write through cache, it is going to update even whatever is there in the memory. So this guy is consistent with memory. However, the problem of inconsistency happens because the private cache of CPU B hasn't been changed to the updated value. So let's highlight that in pink. Problem or the inconsistent. That's the problem, right? So A's cache and memory both contain the new value of 1. B's cache does not. So when B reads the value of X, again, let's say in time step 4, CPU B reads X. What is it going to read? Well, it's going to try to access its cache first. There is going to be a cache hit. It's going to say X is 0, which is wrong. You guys see that? All right, so I hope with this, at least the problem is clear. Let's talk about what is sort of a technically correct and a complete definition of coherence. So memory system is coherent if any read of a data item returns the most recently written value of that data item. So whenever I write to X and read it from X, it will tell me the most recently written value to that memory location X. That's your definition of coherence. Now, this might be very intuitive, it might be very simple, but the reality is a little bit complex, as we have seen earlier, right? Because multiple processors could be reading and writing to the same location in a very, very short duration of time, one after the other, but those read and writes could become very, very complex. When you go to two processors, when you go to four processors, it's going to dramatically change. It's going to become more complex. So let's try to have a little bit more of a classification. All right, what are some of the things that need to be satisfied if if we can call the memory coherent? A memory system is coherent if and only if it behaves as if for any given memory location M, these three criteria are satisfied. 1. Program order is preserved. 2. The view of the memory is consistent. 3. Write serialization. I will talk about each of these three criteria in a little bit more detail, but all of these three have to be met if you want to call the memory coherent. First, preserve program order. What does it mean? It means that write followed by a read by the same processor, right? You have a memory here, address. There are two processors, P1 and P2. P1 is trying to read to a specific address and then trying to read from that same address. Write followed by a read by the same processor with no writes in between returns the value written. So whatever you write, you read the same thing back with P1. So in the previous example, if CPU were to read X after time step 3, it should read the value 1 because it just wrote that, right? In time step 4, say for example, if CPU reads X, it should read 1 because it has a it's 1 is what it has in its private cache, and it should say 1. That is preserving the program order. Whatever you write to the address, you read it back, it should be the most recently written value. But this is in the context of the same processor writing and reading. Next, coherent memory view. This is in the context of two processors, P1 and P2. P1 is writing to a specific address and then later P2 is reading from that address. So if P1 writes X and P2 reads the memory location X, P2 should see the value written by P1 if read and write are sufficiently separated in time. Of course, whenever you are trying to read and write to memory, you should allow for the data to be stable in order for your read operation to go on without corruption. So P1 is trying to write. So if it writes, so let's say if it writes 10 and P2, if it reads 20, then it tells me that there and even if they were sufficiently separated out, you wrote 10 to memory location X and then P2 reads 20, there is a problem. It's inconsistent, right? So that should not happen. In the previous example, we would need a mechanism so that the value of 0 in the cache copy of CPU B was replaced by a value of 1 after the CPU A stores a 1 into memory. You see, that's what we're going to go in here and say, yeah, the problem is because of this, right? So if there was a mechanism in place where CPU A, because it messed with the memory location X, sort of took charge and changed the private caches of all the other processes that are interested in memory location X, that would be really good because that would make sure that the memory reads are consistent. So you have written it, you have written something new to it. So you have to tell others that you have written something to it because others are not going to know. But the CPU that writes to it has to initiate it has to take that responsibility. So that is coherent memory view. One processor writes, the other processor reads. After the write is stable, when those the data that you read is consistent with the data written, that means it is coherent. That means it is coherent memory view. The last criteria in this is write serialization, which is pretty simple. Writes to the same location by different processors are seen in the same order by all other processors. So suppose P1 is trying to write to a location, P2 is trying to write to the same location, right? And if multiple processors are trying to write something to the same memory location, all the other processors should see that write operation happening in that same order. So if P1 writes first, then P2 writes next, every other processor in the system should see that P1 changed it first and then P2 changed it. So in the previous example, CPU B, let's say, stores 2 into memory at address X. After time step 3, the processors can never read the value of X as 2 and then later read it as 1. What does that mean? I have changed it. So there was an X, right? So X was 0 initially. Then CPU A came in and said X is 1. And then CPU B came in and said X is 2, right? After it says X is 2, no processor should be able to read this 1. Like, it should say X is 2. That's what that means. So they should see that writing happen in the same order. I'm of course referring to all the other processors. All right. So if these three criteria are satisfied, then we call it a coherent cache system. Now let's talk about some solutions. There are many solutions. We'll talk about a snooping protocol and a directory-based approach. But there are some software-based solutions, there are hardware-based solutions, there are hybrid solutions as well, which is a combination of hardware and software. The solutions could lie with the compiler or the runtime software support for this. It could be some new instructions in the instruction set architecture called flush and invalidate. Flush could be used to write or all or specified cache lines to memory. So flush out all your private caches and get consistent with the memory. Or we could use invalidate, where it invalidates all the private caches of all the other CPUs. So we'll try to see invalidate message in the snooping protocol in just a bit. Hardware solutions are far more common. One such example is Snooping Protocol, which we will get into here. So, a few things that we need to keep in mind. Snooping Protocol is a hardware solution. And this is this has some limitations because every time you read or write to memory, what you bring from memory to the cache is a full block of memory, right? Block is a collection of words. If you want to change one word, you actually bring the whole block from memory, right? And if a block contains more words, a lot of words, then you're sort of putting the bandwidth between the CPU and the memory, CPU and the cache, you're not using it very effectively. So let's see. It could become a problem when multiple processors are sort of writing and reading to the same location. So every cache in this snooping protocol, every cache has a copy of the data from the block of physical memory and also has a copy of the sharing status of the block. So, but there is no centralized state kept. So every cache, every private cache for every processor has two things. One is the copy of the data that you brought from the physical memory, and also the copy of its sharing status. Next, the caches are all accessible via a broadcast medium. This could be a bus or it could be a network. the cache controllers are going to snoop on the medium, on the broadcast medium, to determine whether or not they have a copy of the block that is requested on a bus. This is essentially saying, if you are going to mess around with a memory location, I want that to be broadcasted on this bus or a network as the medium, so that all the other processors know that you have changed the contents of this particular memory location. Let's take a look at this in a little bit more detail. Snooping Protocol. Each private cache is going to get exclusive access to a block. Block is a collection of words when it is to be written. So if you want to write something to memory, and if it is not there in the cache, you got to get it from the physical memory, right? But what you get is a full block, all the words in that block. And as soon as you know that you're writing to it, you are going to get exclusive access so that others can don't write to it at the same time. And then because you're writing to it, you're going to broadcast an invalidate message on the bus so that everybody else knows that there was some processor that wrote to this memory location. And then the subsequent read by any other cache miss, the owner, which means the cache that originally wanted to write, is going to take ownership and supply the updated value. Let's see that in this example. We have a few columns here. CPU activity, one column. The broadcast messages on the bus in the second column. The CPU A's cache, CPU's B's cache, and then the actual data at memory location. That's in the physical memory, all the way to the right. A blank over here indicates either no activity is done or there is no copy that is cached. So first what is happening is CPU A is trying to read X, memory location X. So of course there is a miss. We are assuming that nobody has X at this point. So that's going to lead to a cache miss for X. That's the bus activity. Okay, so if there is a cache miss for X, CPU A is going to go to memory and try to get the contents of memory location X, which are initialized at 0, into its own private cache. So it gets a 0 from there. CPU B, no activity. Data stays the same because we are just reading, we are not writing here. In the second line here, after CPU A reads, CPU B also reads the same location X. Now what is going to happen? Of course, it is going to be another cache miss because CPU B's private cache doesn't have the memory location X, the block, right? So it's going to say, all right, I need to go and look into the memory. It is still 0, so it's going to bring that 0 into its own private cache. So everybody is consistent so far, 0, 0, 0 in A, B, and data in physical memory. Everybody is okay. Now, CPU A is going to say, write a 1 to X. The moment CPU A writes a 1, it gets exclusive access to that particular block. And it sends an invalid for memory location X message on the bus so that everybody else knows you need to drop that particular memory location content. It's no longer valid. So it wrote a 1, so this guy is a 1. Copy in B, private copy in B is dropped. No cache copy kept. So that gets dropped. It becomes invalid. We have not written this to the physical memory yet. Remember, the only time we are going to write to the other private caches or to the physical memory is when there is a read occurring for that memory location. Unless there is a read that is going to happen, why spend time writing it? So this stays at 0. So the only thing that has a 1 is the private cache of A. But everybody else knows that it is that the same memory location X is going to be invalid as far as their own private cache is concerned. All right, now CPU B reads X. So when CPU B reads X, there is going to be a miss for X. Earlier there used to be a hit, now there is no copy kept, so there is going to be a miss. If there is going to be a miss, who is going to supply the updated value? The owner, which is what? CPU A's cache is going to go ahead and update CPU's B's cache, and it is also going to update the physical memory. That only happens if somebody else, a subsequent read operation happens. So that's your snooping protocol. Questions about this? So we stayed consistent over here. We had a problem in the next line because the private copy of CPU B became invalid, and once a read happened after that, everything became consistent again. Alright, so snooping protocol is this, but it has a problem. Like I said, the block size plays an important role. Block is a collection of words. If you are trying to write to memory location X, all the words in that particular block are going to be brought from memory to private cache, and they will need to be updated. So suppose you bring in the whole thing, you write to this, the entire block has become invalid. So when you read and write from different processors with blocks that are really long, that have many words, that is going to be very stressful for the bandwidth, right, between the CPU and your cache. So let's play out this scenario. Let's say we are snooping on a cache with a block size of 8 words, one block with 8 words, with a single word alternatively being written and read by two processors. So there is a single word in an 8-word block that two processors, say A and B, are writing and reading from. What is going to happen because of that? Well, you are sort of changing, updating, because you are writing, reading, right? So because of that, that is going to, a full exchange of full blocks between the processors is going to occur. I just needed to do this single word update, but because I do this block by block, I'm going to be pushing multiple, exchanging full blocks between the processors, thereby increasing the coherence bandwidth demands. Uh, Ideally, what would you want? Well, ideally, you would want to only update that single word, but that's not how things work. Whenever you have a memory cache miss or cache you miss in the cache, you bring the entire block of memory into the cache. So that's a problem, and it becomes a bigger problem if the number of words in the block are even more than that, right? It's going to put even more pressure on the bandwidth there. So we need a different approach, which is sort of captured in this directory-based protocol, where a global view of coherent state for each block is maintained in a directory, right? So all the blocks, their coherence state is maintained in a global view, right? So everybody has access to that. Instead of broadcasting, the processors are going to send coherence requests to that directory. So there is sort of a one global entity that is monitoring requests and monitoring the coherent state of all the blocks in the memory. So when you do that, so it's still going to require higher implementation because you need to maintain that directory, but that is going to significantly reduce the traffic between the caches, which also means that you can scale this to larger processor counts. The directory is what informs the other participants when there is a write operation that occurs to that specific block. So instead of the owner cache taking responsibility and updating the other person's cache, the directory is what is going to inform other participants that, okay, now your copy, your private copy is no longer current, it needs to be updated. So by doing this global view, you are putting less pressure on the traffic between the caches. So that's a directory based protocol. All right. That is it in terms of lecture today. Oh wow, we went the entire time. All right. So the activity is ready. Please go ahead and answer that. I will be here, and then I will be in my office hours. Um, we are going to have TA office hours from 8 to 9, and then I believe Lawrence has an exam. So he's going to start his office hours slightly later. I think he pushed it back by an hour. So 10 to 11 for Lawrence office hours today. All right. Stop recording.